These are the following statements. BJT is current control device, that is true, but it is having a medium input impedance. FET is a voltage control device and having high input impedance in the low gain bandwidth. BJT FET can be used for amplification, not because with proper biasing only we can use BJT FET as an amplifier. Without biasing we cannot use these devices for amplification. Hence statement 2 is the only correct option here. Hence option B is correct. We'll call the diffusion potential in PN junction is equals to the difference between the Fermi levels of the two sites and expressed in Ohms, that is true statement, and increases with increase in doping levels of two sites and increases with increase. All the statements are true because V, that is built-in potential, is equals to Vt natural logarithm of Na in D divided by Ni square. It increases with increasing in temperature as well as increases with increase in doping concentrations. So option D is correct. For the following NMOS circuit, we have to find out the value of VDS. Here the data is given as VDS is equals to VGS. Hence the given NMOS transistor is in saturation. So for the NMOS transistor which is in saturation, the current equation is given as K into VGS minus VT whole square. So VGS is equals to VDS. So we can replace VGS with VDS. It is 10 power minus 4.5 into 10 power minus 3 VDS minus 1 whole square. That is 5 this. So root 5 VDS minus 1. VDS is equals to 1 plus root 5, which is equals to 3.24 volts. That is option C is correct. Transform of a given Gaussian pulse e power minus et square a greater than 0. So for the transform, that is f of omega is equals to f of t e power minus j omega t dt. So if we substitute this one, it is square e power minus j omega t dt, we will get f of omega as root pi by a e power minus omega square by 4a. That is option A is correct. Mode input voltage for the op-amp network shown below is, suppose I am assuming this node potential is Vi1, this node potential is Vi2. That is Vi1 minus Vi2 is nothing but Vd. So these two node potentials are same. So here if we apply KCL at node VA, there is VA minus Vi2 divided by R2, VA minus V0 by R1 is equals to 0. This is equation 1, this is equation 2. Similarly, VA minus Vi1 divided by R2 is VA by R1 is equals to 0. This is equation 3. So hence V's common mode voltage is nothing but Vi1 plus Vi2 by 2. So from the given expression, Vi1 is Vd by 2, 1 plus R1 by R2. Vi2 is minus Vd by 2 plus Vd by 2 R1 by R2. So if we add these two terms, we are going to get 1 by 2 Vd by 2 R1 divided by R2. That is Vd R1 R2 1 by 2. That is half of the output voltage, that is Option D is correct.
VL and VH for the schemic trigger shown below is, here VH is nothing but whenever V set is equals to plus 12, that is 12 into 33 divided by 1033k plus 3 into 1000k divided by 133k, which is equals to 3.29 volts. Comes to VL minus 12 into 33k divided by 1033k plus 3 into 1000 divided by 1033k, which is equals to 2.52 volts. That is option C is correct. Heterodyne receiver is tuned to a frequency of 0.65 MHz and having an IF frequency of 0.455 MHz. The image interference is at a frequency of, we know if the tuned frequency as well as the IF frequency is known, we can calculate the image frequency as tuned frequency fs plus twice the IF frequency, which is 0.65 plus 455 into 2, which is equals to 1.56 megahertz. That is option D is correct. Discrete memory lasers with source alphabet as S0, S1, S2 with probabilities 1 by 2, 1 by 3, 1 by 6 respectively. Then find the entropy of the sources. Here the entropy can be find out as, that is H is summation of pi log pi. So I is 0 to 2. So if we find out 1 by 2 log base 2 2, 1 by 3 log base 2 3, 1 by 6 log base 2 6, which is equals to 1.46. That is option B is correct.
Of expectation of x is, suppose here assume expectation of x is k, which is a constant. It is going to be a mean value. So expectation of a constant is nothing but a constant, because it is the expectation is nothing but a linear variable. So k is nothing but expectation of x. That is option B is correct.
Of a matched filter, if the input is, here output is nothing but the convolution of matched filter response, which is h of t. Input is x of t, which is given as a rectangular pulse over the duration of 0 to t. So x of t convolved with h of t. So h of t for the matched filter, x of t minus t, so which can be represented as, this can be written as t minus t. So similar to this is also h of t. If we convolve the rectangular duration of pulses, we will get D as a correct option.